Dear students, I am again back, still sipping my cup of tea. But this time we are going to talk about convex functions, examples of convex functions. The most well-known example of convex function is called a linear function. And those whom you have actually gave some thought to your math 102 class at IIT Kanpur, linear algebra, then you must know that any linear function means a function which has the property that f of x plus y is equal to fx plus fy. This is a mistake here, this would be a plus here, and f of lambda x is equal to lambda x. That can be written as the inner product of x with some fixed vector. So fx equal to inner product of a with x. Basically in real 9 it is multiplication, so fx is equal to 2x. So those are called linear functions which satisfies the property that f of x plus y equal to fx plus fy, and f of lambda x is equal to lambda fx, where lambda is any element of R. This is called the homogeneity property, this is called the additivity property. When you add a real number to a linear function, that's called an affine function, and both linear and affine functions are functions which are both concave and convex. The function x square, where x is in the real line and c means convex set on which you define is R. Here the convex set is Rn of course, for linear and affine, the domain. So you try this out to prove from first principles, that is the definition, f of lambda y plus 1 minus lambda x is lambda fy plus 1 minus lambda x. I can tell you you need to do a good amount of manipulation which might bore you off. So just proving things from first principle is not so easy. So to decide whether a function is convex, something else has to be done. Something else has to be done. Okay. Now fx is equal to x ax. It's a quadratic function. Inner product of x, this vector, and then you take the inner product with ax. A is a n cross n matrix which you operate on the vector x. So you get the new vector ax, and you then take inner product of those two. It's called a quadratic form, and if x is greater than or equal to 0 for all x element of Rn, and here the domain is whole of Rn, so then fx is a convex function. A very famous function used in many is effectively used in the barrier function techniques for convex optimization and in proximal point methods, etc., which we need not bother. This function is called the negative entropy function. So here the c is Rn plus plus, because the xi's have to be all strictly bigger than 0 because you are operating log here. So it looks very unlikely that it would be a convex function, but it is a convex function. We will talk about its convexity later on as we speak a bit down. As we go a little down, we will come to, for example, we will give a small result. That is, if you have two functions, f of x plus g of y, x is in say R and y is in say R, and f is convex function and g is a convex function, then if you form a new function h of xy is equal to f of x plus g of y, then the h of xy is a convex function in both variables. And the issue is like this, is that this function is called negative entropy function because the negative of this is a concave function is used as an entropy, the quantity of entropy, and entropy is always maximized. This function f of x1 x2 is minus root of x1 x2 is actually a concave function where c is again R2 plus plus. When x1 is positive, x2 is positive. Actually, if you take the minus of f for this last Cobb-Douglas function, negative Cobb-Douglas function, then we call it Cobb-Douglas function, and f of then the function say h of x1 x2 equal to root x1 x2, x1 to the power half and x2 to the power half is very important in production theory. Actually, this is actually tells you the kind of the production of a firm is product of the capital into the labor, and on the way you have given equal weights to both capital and labor, half. So K is capital to the power alpha and L is a labor to the power 1 minus alpha. You can decide your weights accordingly. And that the production and this quantity is multiplied by some A, some constant, so it doesn't matter. So that is the production function. You want to maximize the production of a firm, and that production function is a concave function. That's very important. And this usually the structure, the standard in standard economics, the structure of the production function is given by this family of Cobb-Douglas function. The family of Cobb-Douglas function is slightly larger, not just this simple x1 to the power half or x2 into x2 to the power half, but it is in the form x1 to the power alpha x2 to the power 1 minus alpha. Alpha is some number between 0 and 1, strictly between 0 and 1, because you have to give some importance to capital, some importance to labor. One of them cannot have zero importance. None of them cannot have zero importance. So let us look into another very important class of functions called strictly convex functions. Strictly convex functions are very important because if they have a minimizer, the minimizer is unique. Strictly convex function satisfies all the definition of the convex function. It is just same as a convex function, but there is one restriction. The inequality here is strict whenever y is not equal to x. For a convex, it is less than equal to. It doesn't matter whether y is equal to x or y is not equal to x. But here, whenever y is not equal to x, the inequality has to be strict. Examples are fx equal to x square, fx equal to e to the power minus x. These are standard examples. But for example, e to the power minus x is a strictly convex function, but it does not have a minimizer. Fx equal to x square, it has an infimum. Its value as x goes towards infinity, the value of e to the power minus x goes towards 0. It has a lower bound, but there is no x for which e to the power minus x is 0. E to the power minus x is always strictly greater than 0. So what I am trying to say here is that this function fx equal to e to the power minus x is a strictly convex function, does not have a minimizer. Fx equal to x square has a minimizer. So if a strictly convex function has a minimizer, that minimizer has to be unique. It cannot be more than 1. Why? Why it has to be unique? It has to be unique minimizer because here is a theorem which tells you that if you take a concave function, it's a convex function over a convex set U, then you are considering the problem of minimizing the function f over a convex set C, which is contained of course in U. We should have written C subset of U. If it has a minimizer, then it has to be unique. So if x1, x2 are two elements and both of them are competing to be a minimizer, both of them say we are minimizer. But if x1 is not equal to x2, that is they are not same, then for any lambda element of 0, 1, please understand in the definition of strict convexity, lambda is chosen strictly between 0 and 1, because if you took lambda, suppose you put 0 here, then it will become fx is strictly less than fx, which is impossible. Even if when y is not equal to x, but if you put lambda equal to 0 there, then it will become fx is strictly less than fx. That doesn't make sense. So lambda has to be chosen strictly between 0 and 1. Now what does it say? Suppose I get two minimizers and both of them are telling, okay, we are minimizers of this strictly convex function, and they are not equal. They are different, distinct. So if I apply the definition of this, I'll get this. F of lambda x1 plus 1 minus lambda x2 is strictly less than this. Now fx2 is a minimum value, global minimum value, and fx1 is the global minimum value. There is only one global minimum value, the function value. So it's equal. That's what we have written. So if I put either fx1 equal to fx2, then it simply means, suppose I put fx2 equal to fx1, then I'll have f of lambda x1 plus 1 minus lambda x2 is strictly less than x1. Now lambda x1 plus 1 minus lambda x2 is element of C because x1 and x2 both are in C, and the convexity of the set C will guarantee that lambda x1 plus 1 minus lambda x2 is in C. Now what does it mean? It simply means that x1 is strictly greater than the functional value at some other point. It cannot be, it is a minimizer. How can it be? So our basic assumption that there are two distinct minimizers is wrong, and hence strictly convex function has a unique minimizer. So with this little information about convexity, we stop our discussion today. I hope you had enjoyed it. Thank you very much.